Hello everyone, my name is Tushar Khod, and today I'll be talking about Text Modular Networks. This is joint work with Daniel Khoshabi, Kyle Richardson, Peter Clark, and Ashish Sabharwal from Allen Institute for AI. So before going into the details of the paper, let's consider this scenario. Say you're a researcher studying Feliformia, and you're interested in finding images containing the species of this suborder. So you go to your favorite visual QA bot, VisBot, and ask it to find you images containing Feliformia. Unfortunately, VisBot does not understand what Feliformia means and does not know how to answer your question. So at this point, if you're a machine learning researcher, you might think, hey, that's an interesting unsolved problem. Let's build a dataset to solve it. And that's what some people have done. And now given this dataset, you might think, hey, let's try to build a model that tries to solve this problem. And you might create a novel model that combines text transformers with visual features with symbolic KBs to solve this. And this is generally how things progress. You identify a new unsolved problem, build a data set for it, and then develop and train novel models to solve these problems, and repeat this process over and over. Unfortunately, this also means that we need to train these new and often very large models for each task from scratch each time. And so the question we ask in this work is, can we instead reuse existing models, that is, stand on the shoulder of these giants to solve these new complex tasks? And so what would that look like? Let's look at our current examples of finding images. Our system should recognize that VisBot does not understand the category Feliformia, and so it can go to TextBot and ask what are Feliformia, and the model returns the answer that Feliformia is a suborder consisting of cats, hyenas, mongooses, and viverrids. At this point, your model can recognize that, hey, cats is a category that VisBot understands, and it asks the VisBot agent to now return images containing cats, and that's what you get. And then you can repeat this for every animal in this species. And so what you're trying to say here is basically, instead of building a new model each time, the system can decompose these complex tasks into subtasks that are solvable by models developed before. And so that's basically the research question we ask here. Is it possible to decompose complex tasks into subtasks solvable by existing models? And what we find is that it is actually possible. We propose a general framework, Text Modular Networks, that can leverage existing simpler models, whether they be neural or symbolic, as black boxes for answering complex questions. We propose an implementation of this framework called ModularQA that can answer multi-hop and discrete reasoning questions. And we show that the resulting model is more robust, versatile, sample efficient, and interpretable. And so before going into the details of this paper, let me first set up the scope of our study. So to answer this research question, we considered two subtasks and models. We looked at the reading comprehension question answering task and used the Roberta model trained on the squad dataset as the first submodel, and we refer to this as SBOT. And then we considered a basic math calculator model that is just implemented using a Python function, and we call it CBOT. We can see inputs to these models on the right side here. The key thing to note here is that SBOT answers natural language simple questions, whereas CBOT answers arithmetic questions in the specific functional form shown here. And so now, given these submodels, we focus on multi-hop and discrete reasoning questions that are solvable by the composition of these two models. Specifically, we looked at HotpotQA and a subset of DROP in this work. We have a couple of example questions from these datasets on the right. Let's specifically look at the DROP example and see how we could use SBOT and CBOT to answer these questions. So the question states, how many years did it take for the services sector to rebound? To answer this question, we would need to first find the difference between the years when the service sector went down and when it rebounded. And we can do that by first asking SBOT, our reading comprehension system, in what year did the service sector rebound? And you get back the answer 2003. We then need to ask SBOT when the service sector started to take a dip, and you get back the answer 2002. Note that in this case, the complex question does not explicitly mention this dip that needs to be asked about, but it is implied in the question. Finally, we can use CBOT to find the difference between these years using its functional format and return that as an answer. And that is basically our proposed Text Modular Network framework, where we train this next-gen model to generate sub-questions for appropriate models in their language. We iteratively call next-gen and these submodels and repeat the process till we find the final answer. And so while question decomposition has been explored before, they often need additional annotations and generate submodel independent decompositions. Neural model network architectures are modular architectures that have been used for question answering, but they do not have this natural textual communication that you can see in the example here, and it does not reuse existing models to solve these datasets. And so at this point, the big question that we have for training text modular networks is how do we train this next gen model to ask the right question to the appropriate models in their language. And so that is a key technical question that we try to solve in this work. Our solution can be broken down into 3 steps. We first learn the language of the submodel. We then decompose complex tasks into sub-questions in this language. And finally, we train NextGen on these generated decompositions. So what do I mean by language of the model? Informally, it is what kind of questions can I ask this model and expect a reasonable output. And so to learn the language of the model, we use the model's original training data. So let's take our SBot here. It's a Roberta model trained on the squad dataset, where given the passage and question as input, it returns an answer span from the input passage. And so to model the language of its questions, we learn an inverse SBot model that generates squad-like questions given the passage and answers as input. Note that the input do not have to be limited to the passage and answers. We could also provide vocabulary hints as input. But for the purposes of this talk, we are going to assume that these inverse models take paragraph and answers as input and produce a question in the language of the corresponding submodel. So now that we have these inverse models for each for SBot and CBot, we can decompose the complex task by using distance supervision hints often used in such datasets. Specifically, given the final answer, we can identify potential intermediate answers that the model would have to hop through to arrive at the final answer. For example, in this question, we can look for dates and numbers in the context, which after a simple arithmetic operation result in the final answer. In this case, if we subtracted 2002 from 2003, we would get the final answer 1. So this tells us what the intermediate answers are for the reasoning process. We can now use our inverse models to generate the questions for the appropriate models at each step. So for example, in the first step, we can use the inverse SBot model to generate the question for the answer 2003, and we get in what year did the services sector rebound. Similarly, in the second step, we would get the question when did the services sector start to take a dip. And for the final step, the inverse CBot model would generate a question in this functional form that is expected by the corresponding submodel. And so now at this point, we have generated the decomposition for these complex questions in the language of the submodel using only distance supervision hints. Training NextGen is just a matter of now training a sequence-to-sequence model that generates the next question given the previous conversation history. During inference, as we showed earlier, we use NextGen to ask the questions and submodels to answer them. There's an underlying search procedure that I won't go into here, but the main thing I want to highlight here is that we do not need answer hints anymore once the NextGen model is trained. And so given this framework, we implemented a system called as ModularQA to solve HotpotQA and DROP questions. Again, I don't have time here to go into the details of this system, but you can check out the demo of this at the URL shown here, and there are more details in the paper too. Next, I would like to talk about the results. First, qualitatively, let's look at some of the decompositions generated by the ModularQA system. Let's look at the second example here from HotpotQA, which says how many children's book has the writer of the sitcom Maid Marian and Her Merry Men written. And so to answer this question, it first asks, using the SBot model, who was the writer on the sitcom. And then given the answer Tony Robinson, it generates the next question, which says how many children's books has Tony Robinson written, and gets back the answer 16. One key thing to highlight here is that these decompositions, these natural language decompositions, are being generated without needing any annotations on the decompositions themselves. Quantitatively, we compare our ModularQA system to dataset-specific models on both the datasets. And so unlike these previous systems, ModularQA is more versatile where the single system works across both these datasets. And while being applicable to multiple datasets, it is still competitive with the dataset-specific modular approaches shown here. Compared to black box models, our system does lag behind, but it gains on other aspects. First, we show that ModularQA is more robust by evaluating it on the contrast test set. These contrast sets are meant to evaluate the model's ability to learn the task rather than the dataset. And we show that our system outperforms NumNet v2, which is a state-of-the-art model on DROP, on this particular contrast set. We also show that we can train a more effective QA system with fewer examples than this black box model. And finally, we show that the explanations generated by our model are more interpretable compared to the previous decomposition-based approach developed for HotpotQA called Decomposition. In a human evaluation, crowd workers preferred, understood, and trusted our explanations much above Decomposition. In conclusion, we propose Text Modular Networks, a framework to compose existing models to solve more complex tasks. We developed ModularQA, an implementation of this framework that can answer multi-hop and numeric reasoning questions. And we showed that the resulting model has multiple advantages over prior work. There are various avenues of future work, such as there are question classes where we can have many spurious distance supervision hints, and that can lead to noise in the question decompositions. For example, the question shown here. Additionally, some complex tasks require submodels for which the underlying subtasks are relatively unexplored. As a result, these submodels are not as accurate, and this can result in noisy answers in each reasoning step. We have released the data, code, and models at the URL shown below. And if you have any questions, please feel free to contact us. Thank you for your time.